In this video, we're going to look at how we can determine the prime factorization of a number. Last class, we established that the fundamental theorem of arithmetic states that every natural number greater than 1 is either a prime number, or it can be expressed as a product of a unique selection of prime numbers. That unique selection of prime numbers is what we refer to as the prime factorization of a number. So it's that product of all these different prime numbers that make up a composite number. In accordance with the fundamental theorem of arithmetic, it is important that the product is made up only of primes and not of other composites. That's the only thing that makes it unique, is if you're using prime numbers. Let's take a look at the whole numbers from 2 to 12. So I've listed them in this table, and I've indicated which are prime and composite. So 2 and 3 are the first ones. They're prime. The first number that's composite is 4. It can be expressed as 2 times 2, which I could write as 2 squared. So that's its prime factorization. 5 is a prime, so we don't have to do anything there. 6 is composite, though, and can be expressed as 2 times 3. So that's its unique product of primes. The next number is 7. 8 can be expressed as 2 times 2 times 2, or 2 cubed, and that's its prime factorization. The number 9 can be expressed as 3 times 3, so 3 squared is its prime factorization. 10 can be expressed as 2 times 5, so that's its prime factorization. 11 is a prime number, and then we move on to 12, which can be written as 2 times 2 times 3. So that is its unique product of primes, and I would write it as 2 squared times 3. So you will notice here that I'm writing my prime factorizations using products of powers. That's just the most efficient way to be writing a prime factorization, is using powers and exponents and things like that. Now, every number can be expressed as a product of primes. For small numbers, it's really easy to find, as you can see here. But for larger numbers, it can be a bit more of a difficult task. So I have a few strategies to show you that will help you find those prime factorizations. So the first strategy I'm going to show you is how to make a factor tree. So we're going to find the prime factorization of the number 42. So the way a factor tree is set up is you look at the number you're working with, and you say, what two numbers multiply together to be 42? And you write them at the ends of these branches that come off this number. So there's lots of things that multiply to be 42. I'm going to use the numbers 7 and 6. So I'll write them in here at the ends of my branches. And now I have to ask myself, are these numbers prime? If the numbers are prime, then I'm going to circle them. And if they're not prime, I'm going to need to split them up further. So 7 is a prime number. And so I am going to circle that number, but 6, on the other hand, is a composite number. It can split up further. 6 can be written as 2 times 3. So I'm going to branch off now, and I'll write those numbers below 6. Then I ask myself, are these numbers prime? And the answer is yes, 2 and 3 are prime, so I'll circle them. All of these circled numbers, which are written at the ends of my branches, they are what we refer to as leaves. So down here at the ends of the branches, these are the leaves that we're looking at here. And so these numbers that are circled, they are the prime factors of 42. And so that means I can write the prime factorization of 42 as 2 times 3 times 7. And that is the unique product of primes that is equal to 42. And now we're going to look at repeated division. So repeated division is a very similar strategy. It's just organizing the information a different way. Now for this example, we're going to work with the number 175. So what we do is we set up a T-chart with 175 in the top right. And I ask myself, what prime number goes into 175? And there's a few options, but I notice, because it ends in a 5, that the number 5 is going to go into that number. So if I divide 5 into 175, I have to ask myself what's left over. So first I write 5 in the top left, and then I'm going to say what's left over when I divide 175 by 5. It may take you a little bit to sort out, but the answer is 35. And so now I have to say, well, what prime number goes into 35? And I have a few answers. I'm going to divide 5 and write it on the left. And what's left over from this process is a 7. And so these prime numbers that I've written out on the left column and at the very bottom of the right column, those prime numbers represent my prime factorization for 175. And so now what I can do is take those prime numbers and use them to make my prime factorization. 175 is equal to 5 squared times 7. So again, I've written it out using powers because that's the more efficient way than writing 5 times 5 times 7. So prime factorizations can be used for a lot of really cool things, but one of the most interesting things is actually finding out the number of factors a number has. So we're going to look at how we can do this process, and the number we're going to use is 175 because we just found its prime factorization. We know it's 5 squared times 7, and so I'll be able to use that to illustrate how you find the number of factors. So we start by focusing in on those exponents on the powers of primes. So I've got 5 squared times 7, so my exponents here are 2, and it doesn't look like there's an exponent on 7, but anytime we don't write an exponent, we know that it is a 1. And so my two exponents here are 2 and 1. So I'm going to write those down separately below. And now what I have to do is increase those by 1. So 2 goes up to 3, 1 goes up to 2. I'm going to multiply those two numbers together to get 6. And that is the number of factors that 175 has. Now, if you're wondering how that all works out, I can promise you there's nothing mystical or magical going on here. This is actually a very logical process that we just went through. What's happening here is we're actually accounting for all the combinations of those prime factors that could create the numbers that divide into 175. So the first factor is 1. The second factor is 5. The third is 7. And then I start to combine them. So 5 times 7 is also a number that goes in. 5 times 5 divides in evenly as well. And so does 5 times 5 times 7, which is 175 itself. And so by taking these numbers and combining them in different ways, I get all the factors of 175. I could use the 5s from the prime factorization twice. I could use them once or not at all. The 7 I can either use or not use. And that's how I get all 6 of these factors. So the prime factorization then can tell us the number of factors that a number has. It can also tell us so many other things. So there's lots more to come from prime factorizations, but I don't want too much too quickly. So we're going to focus on finding the prime factorizations and determining the number of factors. And to make sure that you're understanding these processes, it's very important for you guys to practice your skills. And so that's what we're going to do next. We're going to take the opportunity to practice finding a prime factorization using a method of your choosing and determining the number of factors. We're going to use the number 1,260. Now I'm going to start with a factor tree because that's my preferred method, but I'll show repeated division at the end of this process. So I'm going to start with the number 1,260, and I'm going to write it at the beginning of my tree. Now, I didn't mention this earlier, but we actually refer to this number at the beginning of the tree as the root of the tree. Again, sticking with the whole plant-themed naming conventions of things related to mathematics. So here I'm going to write 1,260 as the root of my tree, and it's going to branch off into 126 and 10, because those were the first factors I spotted. You could have had a different result here, and that's okay. Now, neither of those are prime, so I'm going to split it up further. 126 can split up into 6 times 21, and 10 can split up further into 2 times 5. Now, some of these are prime. I know that 2 is prime and 5 is prime, so that branch of the tree is actually done. But 6 and 21 split up further. 6 splits up into 2 times 3, and 21 splits up into 3 times 7. Now I ask myself, are those prime? And the answer is absolutely they are. So I go and circle all of those prime numbers. And even though they're on different levels of the tree, all of those leaves, all of those circled numbers are the prime numbers that go in the prime factorization of 1260. So I'm going to write it out as 2 squared times 3 squared times 5 times 7. And that's the unique prime factorization for 1,260. Now I can use those exponents to start to find the number of factors. Remember, the rule is increase the exponents by 1. So my exponents are 2, 2, 1, 1. I'm going to increase those to be 3 times 3 times 2 times 2. And if I multiply this out, I get 36. And so that tells me that the number of factors for 1,260 is 36. There are 36 numbers that divide evenly into 1,260. So now I'm going to show you how to do repeated division for this process. And I could pick any prime number to go into 1,260. I know this ends in a 0, so I'm going to choose 2. And when 2 goes in, it leaves 630. And 2 can divide in again. And that's going to leave me this time with 315. So I know it's no longer divisible by 2. So I've written out 2, the number of times it goes in, but this is divisible by 3. So 3 goes into 315 and leaves me with 105. 105 is divisible by 5 and leaves me 21. 21 is divisible by 3 and leaves me 7. And so now that I've ended with a prime in my repeated division, I can circle all the numbers in the left column and the 7 at the bottom, and those numbers make up my prime factorization for 1,260. All right, now it's time for a group activity. So on the last page of your handout, you'll notice I've given you 3 perfect squares. And so what I want you to do in a group of 3 is determine the prime factorization of each of these perfect squares. Now, I'm not going to ask you to do all 3 by yourself. Each person in your group is going to take one number, find the prime factorization using a method of your choosing, and then you are going to exchange your prime factorizations with everyone else in the group. And then what I want you to do is look really closely at the prime factorizations that you discovered and see if you can notice any pattern or any trend that seems to be true for the prime factorizations of perfect squares. There's a few different patterns that you can notice, but there's one in particular that I'm hoping people will be able to spot. So, working within your groups, find the prime factorizations and look for that rule that holds for perfect squares. See if you can find it and tell me what the rule is for next class. That's the end of this video on prime factorizations. I hope it was helpful. I hope it was informative. If there are still some things that are unclear, try going back and reviewing the video again. Remember, you can pause and review again and again to make sure you understand things. If you have questions, don't be afraid to ask your peers. Remember, it's important to ask for help when you need it. We're all learning together. It's a collaborative effort. If you have some questions that are still lingering at the end of class, I'll follow up with you when I return to the school, so don't worry about that. When you're working on the homework exercises today, remember, practice until proficient. Just try your best. That's all I'm asking for. If there's something you're getting stuck on, we can work through that together at lunch or the next time I see you. Have a good day, grade 8s. See you later.